with section 15.8, the final section in this chapter that deals with Lagrange multipliers. You use Lagrange multipliers to find the max or the min of a function on a curve, on a closed curve. All right, so without further ado, let's look at what I just copied this out of your book so you don't have to frantically copy it, and you'll understand as we go along. But the method of Lagrange multipliers is you want to find the maximum and minimum values of a function f of x, y, z, and it doesn't have to be f of x, y, z. It could be f of x, y, but I just put it in a more general case, subject to some constraint g of x, y, z. So we want to find those points for which f attains its max and its min, subject to the constraint that your points x, y, z have to satisfy this equation here. And what the method of Lagrange multiplier says is that if you take the gradient of f and the gradient of g, and remember these are vectors, okay, they're vectors. Gradients are always vectors. We're saying that this gradient and that gradient at any points at which f attains its max or its min have to be parallel. And in order for two vectors to be parallel, the one vector must equal some constant times the other one. Also, your point x, y, z has to satisfy your constraint. And after you solve this system of equations with Lagrange, what happens is that gives you a set of points that are candidates for your max and your mins. And then all you do then is evaluate each of those points at f, and the one with the highest value is your max, and the one with your minimum value is your min. Now, before I go on, I just want to prove this in a very simple case. If you might notice, I did not put the proof in your notes because a lot of you are printing all the notes and then you're losing the forest for the trees. So you just need to watch me, and you don't need to frantically copy. Let me just make a couple remarks. Note, suppose you have some curve, and I'm just going to do it in 2D because I think in 2D it's going to be a little bit easier to follow. Suppose I have g of xy equal to a constant. Now what am I talking about here? You might have an equation like x squared plus y squared equals 25. That's some equation. Now in the xy plane, what does that equation look like? It looks like a circle. And we learned that there are ways that you can get a parametric representation for that curve. In this case, we could let x equal 5 cosine t, y equal 5 sine t for the parametric representation. So in general, let's say a parametric representation for that curve g of xy equals a constant is r of t. Okay, r of t, where r of t is the x component is x of t, and the y component is y of t. All right, now since I'm moving along that curve, I could write this g of xy equals c as g of x of t, comma, y of t is equal to a constant. All right, now I think most of you would agree that g is not changing, so g's derivative would be 0, right? If I take dg dt, it's going to be 0. We know from the chain rule the derivative of g would be the partial of g with respect to x times dx dt, which I'm going to write as x prime of t, plus the partial of y with respect to t times y prime of t. And that derivative is 0. Well, if you look at that, we can look at this as partial of g with respect to x, comma, partial of g with respect to y, dotted with x prime of t, comma, y prime of t is 0. What does that give me? This gives me the gradient of g dotted with r prime is 0. Now notice, this wasn't any extra special point. This was any point which I could find parametrically as I go along that curve. And what I proved just now is this. If you give me a function g of x, y equals a constant, and that's some curve, in this case, in two-dimensional space. What we just proved right here, and we've done it before, but we did, that the gradient dotted with any tangent vector is 0. Which means that you give me a particular point on the curve, the tangent vector goes this way. Okay, that's my r prime of t, all right? But the gradient, when a vector dotted with another vector is 0, what does that mean? They're perpendicular. So that tells me that the gradient is perpendicular to the tangent vector, which means that if I have g of xy equals c, the gradient is always going to be perpendicular to the tangent line to the curve. So right here, the gradient's going to be going that way, perpendicular to the curve. When I have g of xy equals a constant. Now, if you had g of xyz equals a constant, it's a surface. And we could prove, but we're not going to, is that the gradient there is always going to be perpendicular to the tangent plane. We actually did it a few days ago, but I'm just going over this again. All right, so all I proved right now is if I have my function g of xyz, or g of xy equals a constant, the gradient is always perpendicular to the tangent line, to that curve. All right, now what we're doing today is we have some function, f of xy, and we want to minimize it or maximize it subject to the constraint that g of xy is equal to a constant. This is some curve in two-dimensional space. It might look like this. And I'm saying, okay, well, if that's some curve in two-dimensional space, let's let r of t, which I'm going to write as x of t comma y of t, all right, be a parametric representation of that curve. All right, further, I'm going to assume I have a max or a min at the point x naught, y naught. Okay, now since we have to correspond to some point on the curve, that's going to correspond to some point r of t naught. You with me? Okay, so I'm saying assume I found the x naught, y naught where I have a max or a min at that point. Suppose I have a max or a min at that point. Well, notice this function z equals f of xy. Since we're only allowed to use those points that are on the curve, we could look at this as f of x of t comma y of t. Well, I think you can see here, if x is a function of t and y is a function of t, f is really just a function of t. And last time I looked, when a function in Calc 1 of a single variable attained a max or a min, what did you know about the derivative? It was 0, right? So we could think of this as f of t, and we could all say that f prime of t, at least at this t naught where I have my max or my min, must be a 0. But how do I differentiate this function? From the chain rule, the derivative of this function is the partial of f with respect to x times x prime of t plus the partial of f with respect to y times y prime of t, and that must be 0 at t naught because that's where I have a max or a min, because we're assuming we have a max or a min. Well, wait a minute. This is partial of f with respect to x comma partial of f with respect to y dotted with x prime of t comma y prime of t equals 0, which tells me here's my curve. And maybe right here at that point, that's at t equals t naught. Right there, if I look at f of xy at that point, and we'll pretend my x and my y axis are right here, we're pretending that f of, notice this is t naught, but your point's going to be x of t naught comma y of t naught. We're assuming that that particular point, if I find f of xy at that point, I've got a max or a min. Well, we just proved if you have a max or a min at that t naught, the gradient of f dotted with x prime of t naught comma y prime of t naught is 0, which tells me that the gradient of f is perpendicular to r prime of t naught. Well, wait a second. R prime of t naught's here, and I just said the gradient has to be perpendicular to it. A few minutes ago, we proved that the gradient of g is always perpendicular to r prime of t. So what I have here is I have the gradient of f perpendicular to this tangent vector, and I also have, this is gradient of f perhaps, and this is gradient of g. Well, if they're both, and I'm just in two-dimensional space, if you have two vectors perpendicular to the same vector, you know they're parallel to each other. And so therefore, there must, if two vectors are parallel, you have to be able to find some constant, and for some strange reason, mathematicians chose the constant to be lambda, for which the gradient of f must equal lambda times the gradient of g. Now this is only at the point x naught, y naught, where f is attaining its max or its min. Where did that come into consideration? Right here when we said f prime of t naught must be 0. Now, are you responsible for the proof? No. All right, but what you are responsible for knowing is this. If I have a function, f of xy, and I want to maximize or minimize it, subject to some closed constraint, which we're going to call g of xy equal to some constant, then we say if you gave me the list of points, x naught, y naught, where I attain my max or my min, there has to be some lambda where the gradient of f evaluated at that point must equal lambda times the gradient, times the gradient, that's a gradient, of g of x naught, y naught. Now, in a few minutes, this will make a whole lot more sense as we go do some examples. So let's do some examples. The first one I want to do, I think, is example 1 out of the book. So let's go over it. A rectangle. Now, what makes this is a application problem, and what gives students troubles with application problems is that often they have trouble realizing what's the constraint and what do I want to maximize or minimize. But let's just read this problem. I have a rectangular box without a lid, is to be made from 12 square centimeters of cardboard. Find the maximum volume of such a box. Well, to me, the volume is what I want to maximize, right? Let's draw a box. Here's my box. And it has dimensions length, width, and height. What do I want to maximize? I want to maximize the volume, which is just x times y times z. Now, what's my constraint? What is my constraint? My constraint is I only have 12 square centimeters of cardboard. So my surface area must equal 12 square centimeters. Okay, now what's my surface area? Notice since it's an open, it's without a lid, we have the bottom. The bottom is right here. Okay, so the bottom is x times y. Now I have one front. Notice if this is from here to here is z, then also from here to here is z. So I have this front side here is x by z, but this back's also x by z, so I have 2 of them. And then I have a side right here, which is y times z, but I have another one over here that's y times z, so I have 2 of them, and they have to add up to 12. That's my constraint. If I add up the areas of all the sides, no top, that's why you have no t here, you have to get 12. This is my g. That's my constraint. X times y plus 2x times z plus 2yz must equal 12. All right, now, the function I want to maximize is v, but my constraint, the point x, y, z, that's going to give the max or the min of this, must also satisfy this equation here. All right, so we're constrained to a limited domain. What Lagrange's theorem says is that any point x, y, z that's giving me a max or a min for this function must satisfy that the gradient of v is parallel to the gradient of g. That means I have to find some constant that I can multiply the one by to get the other. Now, what is the gradient? Remember what the gradient is. That's the partial of v with respect to x, partial of v with respect to y, partial of v with respect to z, must equal lambda times the partial of g with respect to x, partial of g with respect to y, partial of g with respect to z. Okay, so let's find out what these partials are. Now notice, with this monster equation that I have right here, what this is saying is, if this vector equals some constant times that vector, it means this x component must equal lambda times this x component, this y component must equal lambda times this y component, this z component must equal lambda times this z component. So I must have the partial of v with respect to x equals lambda times the partial of g with respect to x. The partial of v with respect to y must equal lambda times the partial of g with respect to y. And the partial of v with respect to z must equal lambda times the partial of g with respect to z. Now notice I'm a little bit upset right now. Why am I upset? I got to find x, y, and z but I also have a stinking lambda floating around. So when I solve this system of equations, I got to find x, y, z, and lambda. If you have 4 unknowns, how many equations do you have to have? 4. So I go, ooh, where's my 4th equation? It's your constraint. G, in terms of x, y, and z, must be 12. So my constraint is my 4th equation. G has to be 12 in this case. All right, now let's find out what some of these equations are. Okay, now, put a line down the middle of the page. Here's V. V equals x, y, z. What's the partial of V with respect to x? If I differentiate that with respect to x, I just get y, z. We all okay with that? Equals lambda times, now what's g? Here's g. What's the partial of g with respect to x? Well, the partial of xy with respect to x is y. Partial of xz with respect to x is 2z. Partial of 2yz is zippo. You all with me? Okay, now I got to do partial of v with respect to y. Well, if v is xyz, partial of v with respect to y is xz. And that must equal lambda times, what's the partial of g with respect to y? Well, partial of xy with respect to y is x. Partial of xz is 0 with respect to y. Partial of 2yz is 2z. Then we have to do partial of v with respect to z. So looking right here, the partial of v with respect to z is xy. And partial of g with respect to z is, let's see, that's going to be 0. It's going to be 2x plus 2y. And then we have to have g equals 12. xy plus 2xz plus 2yz is equal to 12. And here is my system of equations. Now, sometimes you can solve for x and y and z in terms of lambda. This one is not so obvious to me, and that's why I chose to go over this particular one. One thing that happens a lot of time that's a nice little trick with this, notice I have 4 equations, and I have 4 unknowns, x, y, z, and lambda. So the whole idea here is to eliminate one of the variables. Now, one trick that's a very nice trick with problems like this that you'll come across in the homework. Notice this equation, each of these 3 equations is part of the x, y, z, but it lacks one of the variables. So what I'm going to do is I'm going to multiply this one through by x, and I'm going to take this one and multiply through by y, and I'm going to take this one and multiply through by z. Okay, so look what I have. x, y, z equals blah, blah, blah. x, y, z equals blah, blah, blah. x, y, z equals blah, blah, blah. Well, if all of these equal x, y, z, what do you know the guys on the right-hand side? They equal each other. So I could say that lambda times y plus 2z times x must equal lambda times x plus 2z times y. And also, I could say this one equals that one. Lambda times x plus 2zy is equal to lambda times 2x plus 2y times z. Now you go, Mrs. Strocko, what's that going to do for me? Well, now look here. Could lambda possibly be 0? Well, let's look. Could lambda be 0? Could lambda possibly be 0? Well, notice, going back up here, if lambda is 0, this equation here says x, y, z would be equal to 0, right? Well, if x times y times z is equal to 0, then my volume is going to be 0. Is that going to maximize the volume? No. So, no, lambda can't be 0 to get the maximum. So if lambda is not equal to 0, I can divide through by lambda on both sides. If I divide through by lambda on both sides, on this one I have xy plus 2xz equals xy plus 2yz. And this one I get xy plus 2yz equals 2xz plus 2yz. Well, lo and behold, here, the xy's cancel, so I get 2xz equals 2yz. The 2's cancel, and I get xz equals yz. Z can't be 0. Z can't be 0 because, remember, we're maximizing that volume equation. You let z be 0, your volume 0. I don't think that's going to give you a maximum volume. Well, if I divide through by z on both sides, I get x equals y. You follow what I did? I just divided by z on both sides because z can't be 0. Since z can't be 0, if xz equals yz, then x has to equal y. Now on this side, you have a 2yz here and a 2yz here, so you can subtract it on both sides. So I have xy equals 2xz, and since x can't be 0 because it's the length of a side, if I divide by x on both sides, I get y is 2z. Now you go, Mrs. Strocko, what's that going to do for you? Let me show you what it's going to do for you. Coming back here, let me find the original problem. We had these 3 equations, this one, and this one. Look at my constraint. Here is my constraint. X times y plus 2xz plus 2yz equals 12. Coming back here, since x equals y and y equals 2z, why don't we let y be 2 times z? Let's let z be z. And since x equals y, let's let x equal y, but y is 2z. Let's let x be 2z. You with me? So you follow? Since y equals 2z, if I let z be z, here we have y equals 2z, which is fine. But since x equals y and y equals 2z, we can represent x as 2z. Here I have all 3 variables represented as one letter. And taking that, I can plug it right into here. And I get x times y. So for x, I put in 2z. For y, I put in 2z. For x, I put in 2z. For z, I just put in z. For y, I put in 2z. For z, I just put in z. And I get, let's see, 4z squared plus 4z squared plus 4z squared is 12. 12z squared is 12. Z squared's 1. Z is the length of the side of a box, so z is a positive 1. And well, you can't see that, I apologize. Z is a positive 1. So since z is a positive 1, taking that back up here, x must be 2 times 1, which is 2. Y must be 2 times 1, which is 2. And z must be just 1. And so our maximum volume will be made if I make my sides be, the unit was meters, 2 meters by 2 meters by 1 meter. Okay, I thought that was worth looking at because that was an example in the book, but I thought that might give people a little bit of trouble if they look over it. What did we do? Don't lose the forest for the trees. We said that if I have a function that I want to maximize, subject to a constraint, this constraint must be satisfied and the gradient of what you want to maximize must equal some lambda times the gradient of your constraint. This equation here gave us 3 because the gradient had the 3 partials. So we got one equation from the partial with respect to x, one for y, and one for z, and then we had our constraint. We had a system of 4 equations and 4 unknowns, and I'll be honest with you, the part that's going to give you the most difficulty is the Algebra 2 stuff, solving that system of equations. One trick was making all 3 of the left sides being the same and then setting the right sides equal. Let's look at another one. Use Lagrange multipliers to find the maximum and minimum values of the function subject to the given constraint. Where's my constraint? Right here. This is g of xy is equal to x squared plus y squared is equal to 13. That's my constraint. Okay? So, the gradient of f must equal lambda times the gradient of g. All right? Instead, I don't have to write the whole thing out, do I? This means the partial of f with respect to x must equal lambda times the partial of g with respect to x. The partial of f with respect to y must equal lambda times the partial of g with respect to y. And lastly, the partial of f with respect to z must equal the lambda times the partial of g with respect to z. Plus, we must satisfy the constraint that x squared plus y squared must equal 13. Okay, now before I do this problem, and we're going to do it in a second, notice this function that we want to maximize and minimize, I could write as z equals 4x plus 6y. What's the graph of that look like? What's the graph of z equals 4x plus 6y look like? It's a plane, right? It's a plane. What does the graph of x squared plus y squared equals 13 look like in the xy plane? It looks like a circle. Just now, we're saying the only xy's that you can plug in are the points that are on the circle. And which point or points on the circle will have the highest z-coordinate and the lowest z-coordinate on this plane, because we want to maximize z. I took the liberty of putting this in maple, all right? Here's coming out, this is my x-axis, this is my y-axis, this is my z-axis. In light blue right here, this is the circle, x squared plus y squared equals 13. Circle of radius 13. Here's the plane going forever. Now the plane doesn't have a maximum z, does it? It goes forever, higher and higher and higher. But if I only look at the points on the plane whose coordinates x, y are on that circle, I get this curve in three-dimensional space. We want to get the point here that has the highest z and the point down here that has the lowest z, because we want to maximize that function z equals 4x plus 6y, subject to the constraint that my point xy has to be on that circle. That's what's going on here. All right, now, this one's not hard at all, so let's start thrashing it out. First of all, partial of f with respect to x must equal lambda times the partial of g with respect to x. So what's the partial of f with respect to x? 4. That must equal lambda times the partial of g with respect to x is 2x. Partial of f with respect to y is, partial of f with respect to y is 6. And that must equal lambda times the partial of g with respect to y, which is 2y. And notice I wrote partial of g with respect to z, but there is no z because this function doesn't have a z. It's just a function of two variables. In addition, we have a third equation. Because notice I have 1, 2, 3 unknowns. My third equation is the constraint. X squared plus y squared is equal to 13. Well, first of all, the top equation, I'm just going to divide through by 2 on both sides. So if I do that, I'm going to get 2 equals lambda times x. And if I divide by 2 on both sides here, I get 6 is equal to lambda times y.
3.
Pardon? 3. Okay. Now, lambda can't be 0. How do I know lambda can't be 0? If lambda was 0 here, I'd have 4 equals 0 times 2x, which is 0. Can you have 4 equal to 0? You with me? Can lambda be 0? No, because I'd have 4 equals 0 times 2x. 0 times anything is 0. Can you have 4 equal to 0? No. Right? Lambda can't be 0. Well, since lambda can't be 0 here, I can divide by lambda on both sides, and I get x equals 2 over lambda, and y equals 3 over lambda. This method of attack is used quite often. Get each of your variables, x, y, and if you have a z, in terms of lambda. Now you go, why, Mrs. Strocko? What's that going to get? Help me. Let's just put this in your notes. Get each variable in terms of lambda. Because, don't forget your constraint. Here's your constraint. X squared plus y squared equals 13. Well, if x is 2 lambda, then 2 over lambda squared plus y, which is 3 over lambda squared, must be 13, which gives me 4 over lambda squared plus 9 over lambda squared is 13, or 13 over lambda squared is 13. If we multiply through by lambda squared on both sides, I get 13 is equal to 13 lambda squared, or lambda squared is 1, or what? What's lambda? 1 or minus 1. Right? Lambda could be negative. Now what I suggest you do is down the middle of your page, put lambda is 1 or lambda is negative 1. Coming back here, you have that down already. Let's just put this up here so you can see it all. We have x is 2 over lambda. So x is 2 over lambda, that's a lambda, which is 2 over 1, which is 2. And y is 3 over lambda. 3 over 1 is 3. So we have the point 2, 3 as a possible candidate for max min. But we also have lambda equals negative 1. So x is 2 over lambda. 2 over negative 1 is a negative 2. Y is 3 over lambda. 3 over negative 1 is a negative 3. We have also the point negative 2, negative 3. We have 2 possible candidates for max and mins. How do we decide which one's the max and which one's the min? What do you think? Plug them back in. Let's go back to the original function. The original function is 4x plus 6y. So let's see, f of 2, 3 is going to be 4 times 2 plus 6 times 3. You all with me? Let's move this up a little bit so we can see it a little bit better. 4 times 2, which is 8. 8 and 18 is 26. And if I take f of negative 2, negative 3, it's 4 times a negative 2 plus 6 times a negative 3. Negative 18 and negative 8 is negative 26. So therefore, I have a max at 2, 3. And in fact, I can tell you the maximum value. It's a 26. And I have a min at negative 2, negative 3. We doing okay? The whole idea is get your system of equations, solve them. Sometimes you have to, if you can solve for x and y or x, y, and z without lambda, nobody really cares what lambda is. But a lot of times you have to find out what lambda is first and then do the plugging. Okay, let's do another one. Here's another one. F of x, y, z equals 8x minus 4z, subject to the constraint that x squared plus 10y squared plus z squared equals 5. Notice this is my constraint g, and this is what I want to maximize and minimize. Can anybody tell me, what does the graph of g look like? What is it? X squared plus 10y squared plus z squared equals 5. It's an ellipsoid. So we're saying you have to maximize this function. Subject to the constraint is you got to be on that ellipsoid. All right, now what are my system of equations? Well, we have to have the partial of f with respect to x equal to lambda times the partial of g with respect to x. Okay? We also have to have the partial of f with respect to y equals lambda times the partial of g with respect to y. And the partial of f with respect to z must equal lambda times the partial of g with respect to z. In addition, g has to be 5 in this case. So let's see, what's our partial of f with respect to x? That's an 8. That has to equal lambda. What's the partial of g with respect to x? 2x. What's the partial of f with respect to y? Ooh, 0. Equals lambda times what's the partial of g with respect to y? 20y. What's the partial of f with respect to z? Minus 4. That must equal lambda. What's the partial of g with respect to z? 2z. And then our constraint is that x squared plus 10y squared plus z squared must equal 5. This is my system of equations. Notice my unknowns are x, y, and z. Now, of these 3 equations, which one do you think I'm going to zero in on first? I love zeros. Here's a 0. 0 equals lambda times 20y. All right, so I'm going to look at my system of equations right here. And I have lambda, let's see. I have, look in here, I have, here's my, so you can see a little bit better. All right, I have 0 equals lambda times 20y. Now, if you have 20 times lambda times y to equal 0, what are your options? Lambda could be 0, or y could be 0. You all with me on that one? Okay. Let's fold this in a little bit. How's that? Can you all see that now? Good, 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 good. Okay. Let's suppose lambda is, it's this or this, right? Well, notice if lambda is 0 in the top equation, that would give me 8 equals 0 times 2x, or 8 is 0. Can that happen? No. So since lambda can't be 0, what has to happen? Y is 0. I already got one guy. Y is 0. I know y is 0. Okay? All right, now we know y is 0. We also have, is it okay if I divide through by 2 on both sides here? I have 4 is equal to lambda times x. And if I divide by 2 on both sides here, a negative 2 equals lambda times z. And we have y is 0, we figured out, right? Remember the trick that we used in the last one? Solve for each variable in terms of lambda. So for this one, I can get x is 4 over lambda, y is 0, and z is negative 2 over lambda. Here I have a representation for x, y, and z in terms of lambda. Then what do you think I'm going to do with that? I'm going to plug it into my constraint. We have x squared plus 10y squared plus z squared is 5. Okay? And so therefore, for x, I'm going to put in 4 over lambda. For y, I'm putting in 0. For z, I'm putting in a negative 2 over lambda. So let's see, I have 16 over lambda squared plus 4 over lambda squared is equal to 5. You all with me? So that gives me 20 over lambda squared is 5, or 20 is 5 lambda squared, or lambda squared is 4, or lambda is 2 or negative 2. Then put your line down the middle of the page. Lambda could be 2, or lambda could be negative 2. And then, do we all get that copied? I take that information, and I come back up here, and I go, oh, I had x as 4 over lambda. So if x is 4 over lambda, if lambda is 2, I have 4 over 2, which is 2. Y is always 0. Z was a negative 2 over lambda. Negative 2 over 2 is a negative 1. So my 1 candidate is the point 2, 0, negative 1. But we also had lambda to be negative 2, in which case x is 4 over a negative 2 is a negative 2, y is 0, and z is a negative 2 over negative 2, which is 1. So my second point is negative 2, 0, 1. And then how do we decide which guy's the max and which guy's the min? We evaluate the original function at both of those points. And what was the original function? Go back and find it. The original function was 8x minus 4z. So f of 2, 0, negative 1 is 8 times 2, which is 16, minus 4 times a negative 1 is a negative 4. So that's plus 4, which is 20. And this one's going to be 8 times a negative 2 is a negative 16, minus 4 times 1, which is minus 4, is a negative 20. So therefore, it looks to me like I have a max at 2, 0, negative 1, and a min at negative 2, 0, 1. So this is the point on the ellipsoid that makes f be the maximum, and this is the point on the ellipsoid that makes f be the minimum. Not hard, except if you don't practice these systems of equations, I guarantee you I'm going to blow you way out of the water. Okay, we doing all right? Okay, let's go on to another one. The next one, notice, so far, all our constraints are g of xy or g of xyz equals a constant. The next one is a glimmer from your homework last night. I don't have g of xy equal to 16. I have g of xy less than or equal to 16. What does this look like? X squared plus y squared less than or equal to 16. What is that? It's a circle and it's interior, right? all the points where x squared plus y squared is less than or equal to 16 are all the points on the circle of radius 4 plus everything that's inside. Lagrange is only good for g of xy equal to 16. It is only good for finding if you're subject to the constraint that you're on the circle, not that you're on the circle or inside the circle. So what we're going to do is first we will use Lagrange to find our candidates for max-min on the circle. Then we're going to use from our homework last night to find those points in the interior that are candidates. Remember, to be on the interior, your candidates would be those for which the partial of f with respect to x and the partial of f with respect to y are 0. And then we're going to list all of those candidates, pop it in the calculator, and figure out what f of x, y is for each of those points. The one with the highest value is your max, the lowest value is your min. In fact, let's do the interior first. For the interior, we need the partial of f with respect to x and the partial of f with respect to y to be 0. Well, let's see. The partial of f with respect to x is 4x minus 4. If I need that to be 0, this is a good problem. X is 1 as a solution, because you'd get 4x equals 4, or x equal to 1. The partial of f with respect to y is 6y. If I need that to be 0, I'd get y equals 0. Now let's ask myself, is 1 0 inside the circle? You know, you could possibly have that point someplace outside. Well, yeah, this is a circle of radius 4, and 1 0 is right here, so this is a candidate. 1 0 is a candidate for max-mins. So I'm going to put my candidates right here. Candidates. My first point is 1, 0. And in fact, I can figure out f of 1, 0 right now. It's 2 times 1, which is 2, minus 4 times 1, which is a negative 2, minus 5, it's a negative 7. He's my first and only candidate right now. Okay, now, what do we do next? Next, unfortunately, now we're going to do on the rim. And we're going to use Lagrange. So we need the gradient of f to equal lambda times the gradient of g. Also, we need g of xy to equal 16. So let's see, what's the partial with respect to x? 4x minus 4 must equal lambda times the partial of g. This is g right here. G is that equals, that's 2x. Okay, then we got to do partial with respect to y. That's going to give us 6y equals lambda times the partial of this with respect to y is 2y. And our third constraint is that we have to be on the circle, so x squared plus y squared is 16. Okay? Now, you might be sitting there thinking, oh my goodness, Ms. Strocko, what are you going to deal with? I think I'm going to play with this equation just because it looks like it's the simplest of the three. All right? But as you can see, these systems can get pretty hairy. Now, if this is true, if 6y equals 2 times lambda times y, let's look at that. This is my system of equations that I'm dealing with. I'm looking at the equation 6y equals 2 lambda times y. If I subtract 2 lambda y on both sides, to make life easier for me, do you mind if I divide through by 2? The only way I can solve this is factor out a y. And if two things multiply to give me 0, either this is 0 or this is 0. The old, break out, if you have a product of factors equal to 0, one of the factors must be 0. So I have case 1. Case 1 is y equals 0. Case 2, 3 minus lambda is 0. Now never worry if you throw in an extra guy to be considered as a candidate for max-mins. If you throw in an extra guy, in the end you're evaluating your function at each of those values. You with me? So if you threw in an extra guy, he's not going to be the max or the min anyway. He's just going to get thrown out. So I look and I say, well, if y is 0, since x squared plus y squared must be 16, if y is 0, then x squared plus 0 squared must be 16. That gives me x squared is 16. or x is plus or minus 4. So fine, if y is 0, let's try the point 4, 0 and the point minus 4, 0. So I'm going to put them over here for my candidates, 4, 0 and minus 4, 0. There's two candidates, just satisfying this equation right here. But we also said 3 minus lambda could be 0. Well, if 3 minus lambda is 0, then lambda would have to be 3, right? You all with me? Well, now what do you think I should do with lambda equals 3? If I get lambda equals 3, what do you think we should do over here? Let's try the case where lambda is 3. Coming back up here, I have 4x minus 4 equals lambda, which would be 3, times 2x. And I have 6y equals lambda, which is 3 times 2y. In those two equations where I see lambda, I'm putting in 3. Okay? This one, I have 4x minus 4 equals 6x, or subtract 4x on both sides. 2x is a negative 4, or x is a negative 2. Now, once I got x equals a negative 2, how am I going to find the y that goes with them? Don't forget about your constraint. Since x squared plus y squared must be 16, you can always, since the point has to be on that circle, if I plug a negative 2 in for x, that gives me 4, subtract 4, y squared is 12. So y is plus or minus square root of 12, which your book likes to write as 2 root 3. So we can have the point negative 2, 2 root 3, and negative 2 minus 2 root 3. You with me? So I have two more points, negative 2, 2 root 3, and negative 2 minus 2 root 3. Okay? Now notice, having 6y equals 3 times 2y, that just gives me 6y equals 6y, which is a dead end. That's always true, so there, we can't get any new points from that. In fact, this came from the original saying that 6y had to equal lambda times 2y. So we have all of these points. All of these points. And I took the liberty, just to save us some time, of plugging each of these points in instead of me turning on the calculator and saying I can't see it. So f of 4, 0 I found out was 11. F of negative 4, 0 was 43. F of negative 2, 2 root 3 was 47. And f of negative 2, negative 2 root 3 was 47. So therefore, subject to the constraint that we're on that circle, this function has a max at negative 2, comma, plus or minus 2 root 3, and a min at 1, 0. Okay? Not hard. Okay, let's look at another one. Now, you'll notice in your homework, these say go to section 15.7 and do the exact same problem. If you'll notice, the ones they're telling you to go back to do in 15.7, I did not assign, because I don't like using the method of 15.7 in these types of problems, so we didn't even do them. The derivatives are horrendous when you do it the method of 15.7, just horrendous. You end up with, a lot of times you're taking derivatives of stuff with square roots, and you've got, it's pretty awful. So I chose not to do it. We're only going to do these problems by using Lagrange. Find the point on the plane x minus y plus z equals 4 that is closest to the point 1, 2, 3. Now the way we're going to do this problem, let me show you. You have the point 1, 2, 3 in space. If I take any point at all in three-dimensional space, the distance between this point and this point is equal to square root of x minus 1 squared plus y minus 2 squared plus z minus 3 squared. Now, do you all agree? Now, my constraint is I have to be on the plane. We want to find the point on the plane that makes this equation to be its minimum. Now, the point that makes this equation be the minimum is also going to be the point that would make what's underneath the radical be a minimum. And differentiating without the radical is a whole lot easier than differentiating with. You with me? So the equation that we want to minimize, I'm going to call as big D, is going to be x minus 1 squared plus y minus 2 squared plus z minus 3 squared. I'm going to leave the square root out because the xyz that minimizes this guy will also minimize the square root guy. And what is my constraint? My constraint is that xyz has to be on the plane, and that means that x minus y plus z must equal 4. That's my constraint, because I want to find the point on the plane that makes this distance formula be its minimum. Now I love doing this one because setting it up is the hardest part. This is not a hard problem solving. Okay, so does everybody understand how we got the equation? We want to minimize the distance formula subject to the constraint that we're on the plane. Well, we need to have the gradient of d to equal lambda times the gradient of g. The gradient of d, take that partial with respect to x, is going to be 2 times x minus 1 times the derivative inside, which is 1. That must equal lambda times the partial of that with respect to x is just 1. Partial of this with respect to y is 2 times y minus 2 equals lambda times the partial of that with respect to y is negative 1. Partial of d with respect to z is 2 times z minus 3 to the first times the derivative inside is 1. That must equal lambda times the partial of that, which is 1. Notice I right now have 1, 2, 3, 4 variables. Right now I just see 3 equations showing up. Don't forget about the constraint. Any suggestions how you want to solve this system? This one cries out, solve for x in terms of lambda and plug it into the bottom equation. Solve for x, y, and z in terms of lambda and plug in here. That's exactly what you want to do. So for the top guy, notice I have, if I divide by 2 on both sides, I have x minus 1 equals lambda over 2, or x equals 1 plus lambda over 2. For this guy, if I divide by 2, I have y minus 2 equals minus lambda over 2, and add a 2 on both sides, y equals 2 minus lambda over 2. And the third guy, I'd have, let's circle that, z minus 3 equals lambda over 2, or z equals 3 plus lambda over 2. And I'm going to take each of those and plug them into the equation. X minus y plus z equals 4. So x is 1 plus lambda over 2. Y is 2 minus lambda over 2. And z is 3 plus lambda over 2 equals 4. Okay, to save us a little bit of time, if you simplify this, you will get 3 halves lambda equals 2. Or lambda, if you multiply by 2/3 on both sides, is 4/3. And then plugging them in, x is equal to 1 plus 1/2 lambda. That's 1 plus 1/2 times 4/3. That turns out to be 5/3. Y is 2 minus lambda over 2. So that's 2 minus 1/2 times 4/3. That turns out to be 4/3. And z is 3 plus 1/2 lambda. That's 3 plus 1/2 times 4/3. You can write that as 3 2/3 or 11/3. And so therefore my point is 5/3, 4/3, 11/3. Now notice I know that that point is going to be the closest point, because if you go back and see what the problem is, you want to find, you have a plane and you have a point, and you want to know the point on the plane that's closest to that point. There is no point furthest away because the plane goes forever further and further away, and so that's our closest point. Okay. This one's real easy, so it's worth doing. In fact, I think it's in your homework also. Find the 3 positive numbers whose sum is 100 and whose product is a maximum. All right, I've got 3 numbers, so I'll call the 3 numbers x, y, and z. Notice they're 3 positive numbers, so they're telling you that x, y, and z are all greater than 0. X is greater than 0, y is greater than 0, z is greater than 0. X, y, and z cannot be 0. If their sum is 100, that's your constraint. That's your g of x, y, z. X plus y plus z has to be 100. And what you want to maximize or minimize is their product. Okay? Going through and doing this, notice what we have here. We have the gradient of f, or let's say the partial of f with respect to x is yz, and that equals lambda times the partial of that with respect to x is just 1. So we have yz equals lambda. The partial of f with respect to y is xz, and that equals lambda times 1. So I have xz equals lambda. And then lastly, we have xy equals lambda. Okay, now if you look at that problem, we could try to solve like for x in terms of whatever, but I'm looking at this one. This one cries out. When you see each of them has a part of the x, y, z. Let's multiply this one through by x, this one through by y, this one through by z, and I have this equals x, y, z, this equals x, y, z, this equals x, y, z. Therefore, lambda x must equal lambda y, and lambda y must equal lambda z. They all must be equal to each other. Okay? You with me? Now, lambda can't be 0, because if lambda is 0, then y or z is 0. And y and z are both positive. So if I divide through by lambda, I get x equals y and y equals z. Well, shoot, that means they all have to be the same, so I can represent them all as x. So the constraint was they had to add up to 100. So if x plus x plus x has to add up to 100, x is 33 1/3. A third would be nice. And therefore, x equals y equals z equals 33 1/3. So that's what the numbers have to be to maximize their product. Okay, we have one more quick little concept. And you have one of these in your homework, and you will be getting a Maple worksheet soon that has this also. Sometimes you have a function of 3 variables, and you're subject to 2 constraints. Remember, this is a surface in 3-dimensional space. This is a surface in 3-dimensional space. So you're subject to the constraint that you're in the intersection of those 2 surfaces, which will produce a curve. Okay? If that happens, the gradient of the function that you want to maximize or minimize is equal to lambda times the gradient of the first constraint plus the Greek letter mu times the gradient of the second constraint. Okay, and in your book, I decided, you guys are a little bit spent at this point. I'm just handing it to you on a silver platter, but they have a lovely discussion on why this is true in terms of the gradient being perpendicular to level surfaces and that type of thing. So let's just do one more example of this before we call it quits. We have the function f of x, y, z, which is 3x minus y minus 3z. We want to maximize this function subject to the constraint that we're on this plane and we're on this cylinder. All right, now notice what we will call this guy G and this guy H. So remember what we just wrote down. The gradient of f must equal lambda times the gradient of G plus some mu times the gradient of H. Okay? So, notice now we have 5 unknowns. You're going to get 3 equations from the partials, and then your 2 constraints are your 4th and your 5th equation. So we have to have the partial of f with respect to x equals lambda times the partial of g with respect to x plus mu times the partial of h with respect to x. And then you'll have it for in terms of y and in terms of z. You all with me? Okay, so let's write down what these equations are. First one, partial of f with respect to x, thank goodness, is just a 3. That's good. Equals lambda times, what's the partial of g with respect to x? 1. Plus mu times the partial of h with respect to x is 2x. Now I'm going to do it with respect to y. Partial of f with respect to y is a negative 1, equals lambda times partial of g with respect to y is 1, plus mu partial of h with respect to y is 0. So this part's just a big old 0. Partial of f with respect to z is minus 3, equals lambda times partial of g with respect to z is a negative 1, plus mu times partial of h with respect to z is 4z. Notice right now I just have three unknowns and, I have five unknowns, three equations. Your other equations come from your two constraints. X plus y minus z is 0, and x squared plus 2z squared equals 1. So here are my five unknowns, lambda, mu, and x, y, z. Well, which equation do you think I'm going to jump on? That middle one. Look what it tells me. It says lambda equals a -1. That's good. Let's plug it into the top equation. That gives me 3 equals a -1 times 1 is a -1 plus mu times 2x, or if I add a 1 on both sides, 4 is equal to 2 times mu times x, or 2 is equal to mu times x. Do we all see that? So I'm going to write that down here. 2 is equal to mu times x. Now looking at equation 3 here, since we know that lambda is a -1, I have a -3 is equal to a -1 times a -1 is 1 is equal to plus 4 times mu z. Subtract a -1 on both sides, and I get mu times z is a -1. -1 equals mu times z. Okay. Now notice, mu can't be 0, because then you'd have 2 equals 0. That's not going to happen. So I can solve for x in terms of mu. X is 2 over mu, and z is -1 over mu, just like we did before. And then what equation do you think I'm going to plug that into? I think this one right here. My one constraint with the x's and the y, and just x and z. So I have x squared plus 2z squared equals 1. So x is 2 over mu. Z is -1 over mu. So let's see, I have 4 over mu squared plus 2 times 1 over mu squared is 1. So this is 4 over mu squared plus 2 over mu squared. 6 over mu squared is 1, which gives me 6 equals mu squared, or mu is plus or minus square root of 6. Coming back here, I have put the line down the middle of the page. Mu is square root of 6, or mu is minus square root of 6. So here x is 2 over mu, so it's 2 over root 6. Y, no y, z is -1 over mu, so it's -1 over root 6. Here x is 2 over mu, that'd be a -2 over root 6. And z is -1 over a minus root 6, so it's 1 over root 6. So far I have x, z. I need to get y. I need to get y. How am I going to get y? Mrs. Strocko, will she ever end? How are we going to get y? This is my equation of original ones. I haven't used this yet. I haven't used that constraint. That constraint says that y must equal minus x plus z, right? If I take this constraint, x plus y minus z is 0, y is equal to subtract x and add z on both sides. Y is equal to minus x plus z. So if y is minus x plus z, my y is -2 over root 6 plus a -1 over root 6, which is a -3 over root 6. So my first point is x is 2 over root 6, y is -2 over root 6, and z is -1 over root 6. And the last one, this point right here, since y is minus x plus z, my y would be 2 over root 6 plus 1 over root 6, which is 3 over root 6. Oh, wait a minute, that's a -3 right here, 3. Because it's x, y, and z. I apologize. And this point is -2 over root 6, 3 over root 6, and 1 over root 6. So if we evaluate this function, the first guy evaluated, is going to give us square root of 6 over 3, and so he's going to be our max. And I already took the liberty of plugging him in. This is equal to minus root 6 over 3, and this is going to be our min. Also, if you look in the back of the book, and I know you're tired, so I don't want to continue, but if you look in the back of the book, they don't have the points written this way. They have the points written as square root of 6 over 3, minus square root of 6 over 2, and minus root 6 over 6. You all realize what they did, right? They just rationalized the denominator. I know this was a difficult section to go over because the equations are tedious. Let me warn you that you need to suffer at solving these equations. Watching Mrs. Strocko is not going to cut it when you take the test. If you haven't done like 3 or 4 and at least two in each kind of the homework, I'm going to blow you out of the water, and I guarantee you that there will be at least 2 Lagrange problems, maybe 3 on the test. So you need to practice. The ones I suggest for you to look at are on pages 1006 to 1007, and you can do any of these. And pick 2 or 3 in each section to do. If you have trouble solving the equations, you bring the equations to me and let me see what you're doing and if your logic's working. Also, there's no way anyone can write out all these problems in the chapter review. I don't expect you to. But in the chapter review, these are the types of problems that are going to show up on the test. I suggest you study the practice test first. And then, when you do the practice test, you don't look at my answer key. You actually take the test, put the answer key someplace else. After you've taken the whole test and thought about it, then you look at the answer key. It's so easy to sit there and nod your head and say, oh yeah, I remember Mrs. Strocko doing that. Oh yeah, oh, gradient, piece of cake, I remember how to do it. Then you get in the test and you're like, oh, how did she do it? Well, because I did it, I remember how to do it, but you just watched me do it. It's not going to stick home. You've got to practice. And then after you go through the practice test, after you come and see me and I help you explain how to do it, then the chapter review are wonderful extra problems to go back to solidify what you know and what you don't. All right, those of you at home, good luck studying and good luck on your test. And I'll see you guys next time when we start chapter 16. Bye-bye.